energy level equation for the hydrogen atom. In the HSC physics course in module 8 from the universe to the atom, looking at the quantum mechanical model of the atom, there's an expression that you need to know for the HSC. Here it is. E sub n is minus 13.6 EV times z squared over n squared. Looks a bit complicated, it really isn't. Now, as you know, hydrogen is the simplest atom. It's the simplest element in the universe. It's got one proton and one electron. Now this, I should specify, this is the Bohr model of hydrogen. So Niels Bohr was a Danish physicist who came up with this atomic model in 1913. Now let me provide some context, historical context, and let me show you where this thing comes from. So going back to the early 1900s, scientists, they struggled to explain the different spectral lines of hydrogen. So in other words, if you take hydrogen, let's say hydrogen gas, and you heat it up, you'll get different lines, different colors of light. You wouldn't get a continuous spectrum like a rainbow, you get specific lines. Now, it was in 1913 when Bohr came up with this model to explain this. And he successfully did so for hydrogen. What his model couldn't do, however, was explain multi-electron atoms, anything beyond hydrogen, like helium and lithium. Okay, there were other problems too, but that was the main issue. And Bohr's model was a semi-classical model. Okay, it was on the right track. It wasn't fully, completely correct, but it was on the right track. Semi-classical because it combines classical physics and quantum physics. Okay, quantum physics describes the physics of the very small, of particles and atoms. Classical physics describes the macroscopic world, the world of the very large. So humans, cars, planes, and all that. Going back to Bohr's postulates, this is part of the syllabus. So here are the postulates. First postulate, electrons orbit the nucleus in circular orbits. It's much like planets orbit the sun. Second postulate. So a postulate is an assumption or a suggestion. Second one was that electrons orbit the nucleus in quantized energy levels. Quantized means discrete or fixed, I should say. Okay, you can't have orbits like this all over the place. You can have orbits that are like this. Okay, fixed in radius, let's say. Okay, they do so without emitting any energy. Okay, so there's stable orbits, much like the planets orbit the sun. You don't see Earth hopping out of its orbit every now and then. Another postulate is that energy is only emitted or absorbed when electrons jump between levels, between energy levels. And the fourth postulate, now sometimes it's written as three postulates, okay, because the first postulate is assumed, or sometimes it's written as four postulates. I'm just going to write the four postulates here. The fourth postulate is that angular momentum is quantized. Now, angular momentum, typically written as L, is mvr, and that's nh bar. What's angular momentum? So going back to the hydrogen atom, we know from everyday experience momentum, normal momentum, classical momentum P equals mv, is a measure of how hard it is to stop something moving, basically. So a bullet has more momentum than, let's say, a soccer ball that's flying through the air, because the bullet has high velocity. So anything that's in circular motion has angular momentum. Okay, it's got a mass m moving at velocity v, and it's at some radius r from the center of motion. That's angular momentum. N is an integer. Okay, a whole number, 1, 2, 3, etc., etc. H bar, this is what's called the reduced Planck's constant. Reduced because it's simpler to write this than this. So H bar is just h over 2 pi. Now, where this came from previous work by a guy named John Nicholson, if I'm not mistaken, before Bohr. And Nicholson was using this to describe electrons in a hydrogen atom. And Bohr took his idea and applied it to his model. Okay, just think of a circle, okay, 2 pi r radius, 2 pi r circumference. H is Planck's constant. It's a fundamental constant, the basic constant of quantum physics. It's 6.626 times 10 to the minus 34 joules seconds. They're the units. So what Bohr was saying was that every energy level in hydrogen, so let's say, so n equals 1, okay, this is called the principal quantum number. Principal quantum number tells you which energy level an electron is in. Okay, so n equals 1 means that's the first energy level. It's also known as the ground state. Okay, the very bottom, the lowest energy state in the hydrogen atom. Okay, I'll put the plus here as the nucleus. Okay, that's n equals 1 there. Then there's n equals 2. I'm sure you get the idea, so on and so forth. The higher up you go in terms of n, the more energy in that particular energy level. So in other words, the angular momentum for the first shell is 1 times h bar, h on 2 pi. I'll write it like this. It's just h on 2 pi. Angular momentum for the second energy level is 2 times h on 2 pi. 2's cancel out, you get h on pi. Angular momentum of the third level is 3 times h over 2 pi, and you get the idea. Okay, so the angular momentum increases as you go up in energy level, which is what's expected, right? You need more energy to maintain that orbit, in other words. Okay, let me now derive this formula here, okay, where this comes from. Now, for the HSC, I'd recommend you just memorize it, okay? Sometimes you don't have time to derive it or under exam pressure. Just memorize it. It's not on the formula sheet. So let me show you a simple derivation. It's actually not that hard. Okay, let's start with Coulomb's law. So Coulomb's law is a law that describes the electrostatic force between two charged particles. So in this case, it's the electron and the proton. Coulomb's law is this. So here it is from year 11 physics. Electrostatic force is 1 over 4 pi epsilon naught Q1 Q2 over R squared. This here is a number, sometimes called K, to make life easy. All of this is equal to 9 times 10 to the 9. Now these, so 4 pi is 3.14. Epsilon naught, this describes how much resistance is encountered when forming an electric field in vacuum. Okay, it's a number, it's 8.85 times 10 to the minus 12. Okay, but 9 times 10 to the 9, say to students, just memorize that number, it's just easier, instead of going back and forth on the formula sheet, on the data sheet I should say. Q1 and Q2, they're the charges of the two particles, and R is the distance between their centers. Let's say that's the proton, and that here is the electron. Okay, that's R there. Now the nucleus, I'm going to write this in a different way, slightly different way. Nucleus has a charge of plus capital ZE. Z is the atomic number. Okay, atomic number tells you how many protons there are in an atom, or electrons. Atomic number is 1 for hydrogen. Okay, it's got 1 proton. And E is the basic elementary charge. Okay, the elementary charge is 1.602 times 10 to the minus 19 coulombs. So we can rewrite Coulomb's law as follows. F equals 1 on 4 pi epsilon naught ZE times E over R squared. Okay, E and E, fundamental charges, there's two charges. So we simply get this ZE squared over R squared. That's Coulomb's law. Let's now equate this to the centripetal force, because Coulomb's law is what provides the centripetal force, okay? It provides the electrostatic attraction between the two particles, the proton and electron. So let's just write K instead, I should say. K ZE squared over R squared is mB squared over R. That's the centripetal force. Now, from Bohr's quantization of angular momentum, postulate number 4 from here, we know the following. mvr is nh bar. So therefore the velocity is just nh bar over mr. That's the velocity of the electron. Let's substitute this into this. And we can also use the conservation of energy, okay? So conservation of energy states that the total energy in any system, any two objects in this case, the electron and proton, is the sum of the kinetic energy and the sum of the potential energy. Now the kinetic energy is half mv squared. Potential energy is simply provided by U. So U, we're going to figure out what U is. Skipped a step here, so let's go back to this here. So here's what we get. M over R. V is NH bar over MR squared. And that's 1 on 4 pi epsilon naught ZE squared over R squared. If we simplify this expression here, we get N squared H bar squared over M R cubed is ZE squared over 4 pi epsilon naught R squared. If we multiply both sides by R cubed, we get N squared H bar squared is ZE squared over 4 pi epsilon naught R. Solving for R, R is 4 pi epsilon naught N squared H bar squared over MZ E squared. So that's the radius of the circular motion for the electron around the proton. This derivation is a bit rigorous. I just want to show you where it comes from, as requested by some students. So going back to the kinetic energy expression, K is a half mv squared. Let's plug in for mv squared, this thing, ZE squared over 4 pi epsilon naught R. So K is just a half times ZE squared over 4 pi epsilon naught R. And that is that'll give you ZE squared over 8 pi epsilon naught R. Now the potential energy of an electron in an electric field is given by minus 1 on 4 pi epsilon naught ZE squared over R. Okay, in other words, this is the the electric field stores energy, okay? It's potential energy here. That's from year 11 physics. So therefore the total energy E, subtotal, is just K plus U, and that's ZE squared from above over 8 pi epsilon naught R minus ZE squared over 4 pi epsilon naught R. Doing the maths, you get minus ZE squared over 8 pi epsilon naught R. Let's now plug in the equation for R, this thing here, into this. And here's what we get. E total is minus ZE squared over 8 pi epsilon naught times MZ squared, MZE squared over 4 pi epsilon naught N squared H bar squared. Simplifying, you get minus Z squared e to the 4n over 8 pi epsilon naught squared times H bar squared times N squared. Now this thing here, this is the general Bohr formula for hydrogen-like atoms. Also written like this. Minus 13.6 electron volts times Z squared over N squared. And I'll highlight these here. These are the numbers. E to the 4m, 8 pi epsilon naught squared, H bar squared. So if you compute those, you get minus 13.6 electron volts. Very lengthy derivation. That's why I suggest you just memorize this expression. Okay, you're not going to be able to derive this in a trial exam or HSC exam. It's too time consuming, but that's where it comes from, as some of you have requested to see the derivation. There's other ways to derive it, but this is one of the best ways, I think. So to run you through it again, briefly, Coulomb's law, you start with this. 1 on 4 pi epsilon naught Q1, Q2 over R squared. You rewrite it in terms of Z. Now Z is the atomic number. Okay, it's 1 for hydrogen. So you put in the Z anyway, you can, because it's just 1. Put it inside the expression, you're not going to change anything. You get this here. Then you equate the Coulomb's law with the centripetal force, because Coulomb's law of electrostatic attraction The attraction, the very attraction between the proton and electron is what provides the centripetal force. The electron's able to orbit because of this. Equate these, then you use Bohr's postulate of the quantization of angular momentum, rearrange for V. Then you plug in V into this. And then you find this expression here. So you get this, and then you equate it to Coulomb's law. Okay. Apologies, no. You substitute it into Coulomb's law, into the centripetal force formula, the V expression. You get this here. Then you simplify until you find an expression for R. Then you, using the kinetic energy formula, you plug in what mv squared is to get this. And you know the electric field strength is just given by this. And then you plug it into the conservation of energy. And eventually you get this mess here, which is just this thing here. I should also specify, this is also known as the this formula here, ionization energy of an electron in hydrogen. You can do calculations with this in the HSC. They might ask you this. You need to, let's say, work out the ionization energy of the electron in the second shell. So what you do is use the formula, which is this. You simply plug in N for 2. So E sub 2, the energy in the ionization energy of the electron in the second shell. Ionization energy, remember, is the energy required to ionize the atom. Ionize means to knock off the electron. It's just minus 13.6 times Z squared. So Z is 1 squared divided by 2 squared. And putting that into your calculator, you get this 3.4 electron volts. What you'll find is the energy gets less and less as you increase the energy level. Okay, it makes sense because it's harder to pull an electron away if it's closer to the nucleus, okay, because of the electrostatic attraction. So N equals 1. The energy, if you calculate it, is minus 13.6 electron volts. As you go higher up, it gets less and less. It's much easier to remove because there's less electrostatic attraction between the electron and proton.